Hey everybody. In this unit we will talk about bonding. Bond is a force that holds two things together. We will go through a slideshow that takes care of covalent and ionic bonding, their structures, their physical properties, molecular shapes, intermolecular forces, you know. So that's we will cover these topics. This particular lesson is about ionic bonding. So we're starting with ionic bonds. As we move further along, we will talk about covalent bonds, molecular shapes, intermolecular forces, metallic bonding, physical properties. These two are for higher level classes, so we're not going to worry about hybridization or delocalization of electrons. This unit will end with a test that you know is 60% of your grade. This particular test will include the questions from atomic structure and periodicity that we have covered already. So this test will be a cumulative test of 3 units. Alright, so let's start with ionic bonding. Before I start, I want you to reflect what is your understanding of ionic bonding. So take a second and tell me, you think about it, what do you know so far what an ionic bond is about? So, ionic bond is an electrostatic attraction between two oppositely charged ions. You have a positive ion and you have a negative ion. So, we call it a cation. The reason we call it a cation because it is collected or it is attracted on cathode, which is a negative electrode. So, that means it has a positive charge. So, since it gets collected or it is attracted towards cathode, we call it a cation. And that cathode has a negative charge. And we call this anion. The reason we call it anion because it is collected on anode, which is a positive electrode, and that means it has a negative charge. So a cation and anion attract each other, and that is that electrostatic force of attraction that holds the two together is called ionic bond. You must understand the word electrostatic attraction between two oppositely charged ions. So here you see an example of lithium. Lithium has 1 valence electron. Oxygen has 6 valence electrons. So that means if I need to complete the octet, which I will be talking about in a few minutes, oxygen needs two more electrons to complete the octet. That means oxygen needs to be bonded with 2 lithiums. So each lithium is going to lose 1 electron to oxygen. So oxygen will be -2, lithium will be +2. You see oxygen -2, each lithium is +1. So the formula is, the compound is lithium oxide. Ionic bonds typically form between a metal and a non-metal. So as you know that lithium is a metal and oxygen is a non-metal. So an electrostatic force of attraction between a metal and a non-metal is called ionic bond. We usually refer them as salts. All ionic compounds are called salts. No, the question here is that how the cations and anions are formed. Well, another thing, ionic compounds are called non-directional. And covalent compounds are called directional. Okay, because their ionic compounds are described as non-directional because each ion is attracted to every other ion in opposite charge. So there is no positive direction, specific direction. Like chlorine, in a covalent bond, chlorine is directed to this side. This is they're kind of angled or facing each other. But in an ionic bond, each positive ion is attracted to any negative ion, so they're called non-directional. No, next question is that why ionic bonds are formed, what makes them go through this oxidation and reduction. So the formation of an ionic compound typically involves a reaction between a metal and a non-metal. We just learned that. and it is based on their electronic configuration. So the electron arrangement, let's take an example of sodium. So electron arrangement of sodium is 2, 8, and 1, and electron arrangement of chlorine is 2, 8, and 7. So you see that in the ionic bond of sodium chloride, the valence electrons from the chlorine from the sodium, third, this is first energy level, second energy level, third energy level. So if I write down the electronic configuration, it is 1s2, 2s2, 2p6, 3s1. For idealist electronic configuration, it is 1s2, sorry, it should be it, 2s2, 2p6, 3s2, 3p5. And if I do the orbital diagram, if you remember orbital diagram, for only p, I'm only doing it for p, you have 1 according to the Hund's rule, and then, so what you see here is that this is 3px, this is 3py, this is 3pz. So you see that the electron from the 3s orbital of, I'm using the word orbital, that the electron from 3s orbital of sodium is transferred to one of the unpaired 3p orbital. Okay, when it happens, sodium ends up with 2 and 8 because this electron is gone, and chlorine ends up with 2, 8, and 8. So do you see that both of them have gotten a noble gas configuration? The sodium atom has the noble gas configuration of neon, and chlorine atom has the noble gas configuration of argon. So this drive of metals to get the noble gas configuration, where to lose or gain electrons, to get the noble gas configuration is called octet rule. Okay, octet rule means they want to have 8 electrons in the outermost energy level. So if you have like 3 energy levels, they want to have 4 pairs in there. So total of 8 electrons in the outermost energy level. That's called octet rule. We'll talking about it in a minute. So this is the reason ionic bonds are formed. They want to follow the noble gas configuration. They want to complete their octet. So metals lose electrons, non-metals gain electrons. The next thing, hold on, let me also follow this. So we see that group 1 elements, all elements in group 1, they have 1 valence electron. So they all will lose 1 electron. So they have a positive 1 oxidation number. All elements in group 2 have 2 valence electrons. Okay, electrons in the outermost orbital. So they all will lose 2 electrons. So we have oxidation number of positive 2. And then aluminum has a positive 3 because it's going to lose 3 electrons. Transition metals have multiple ions. They can lose 2 or they can lose 3. So sometimes it depends which is the one more stable state for them. So although it's very interesting if you do the electronic configuration of iron, you will see that iron positive 2 has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. So every electrons, 1, 2, 3, 4, 5. So you have 1, 2, 3, 4, 5, and 6. I'm doing orbital diagram for D. Okay, because 4s2 electrons are gone. 4s2 electrons are gone. I'm doing it positive 2, iron positive 2. That is electronic configuration. But this is not as stable as this one is, where it has 3d5 valence electrons. That is more stable state. So that's why iron positive 2 can be easily oxidized further to iron positive 3 because this is more stable electronic configuration. Okay, because that means each one will have only 1 electron. So this is more stable electronic configuration. So that's why they have multiple oxidation states. Okay. Same thing on the other side of the periodic table where you have non-metals. We know group 18 doesn't play any role. They don't lose or gain electrons. Group 17, they have 7 valence electrons, so they all gain 1. Group 16 have 6 valence electrons, they all gain 2. 15, they all gain 3. So these are their oxidation states. Okay. So we need to know the oxidation numbers. The for I'll do it again. Excuse my drawing skills here. So 1, 2, then we have 3 to 12. We have 13, 14, 15, 16, 17, and 18. So based on the valence electrons, you should be able to figure out what the oxidation number is. So oxidation number here, they all have one valence electron. So this positive 1, positive 2, positive 3. This is negative 1, negative 2, negative 3. You know they have they all have one valence electron. They have two valence electrons. They have three valence electrons. This is 4, 5, 6, 7, and 8 valence electrons. So these are the valence electrons, and these are the oxidation numbers. Oxidation state. So you should be able to figure out the oxidation states. So I can tell easily that all the metals will lose electrons. Okay, they go through oxidation and they make cations, positive ions. All the nonmetals, they go through reduction. They make anions or negative ions. Okay, the elements that are in the middle, you know, the elements that are group 14, they have a complete, you know, paired electrons. So they have a very stable electronic arrangements. So these elements will only react with very highly active, you know, because they have 4 valence electrons. So they have paired electrons in their outermost ring, so it's already stable. So they only react with very active elements. You know, they can react both sides, but they will react very active elements. So carbon and silicon have outer shells which are half full. These two elements generally do not form simple ions. They actually form covalent compounds. So carbon and silicon are usually covalent. Okay, they will not make ionic bonds because, as I just said, that they have half full octet. So they will only make covalent bonds. So this is kind of talking about that we see that everybody is struggling to get 8 valence electrons. And that's where the discussion will lead into the octet rule. So in 1920, Gilbert Lewis was a scientist. He realized that a lot of atoms in the compound, they try to achieve a noble gas configuration. Okay, and he see that they lose valence electrons or they gain valence electrons, but the whole purpose of losing or gaining valence electrons is to get the noble gas configuration. I'm sorry, I didn't mean to do that. Noble gas configuration. And he said that tendency is called octet rule. Okay, so the octet rule of electron is 4 pairs of valence electrons arranged around the atom. So any atom that you have 4 pairs: 1 pair, 2 pair, 3 pair, and 4 pair. So every element here is trying to have 4 pairs around the atom. Okay, that's called octet rule. But this octet rule is not observed for the elements beyond the second period. You know, so beyond the second period, like for these ones, there are a lot of exceptions. Okay, but up until first period and the second period, they all follow the octet rule. They all try to get 8 valence electrons. Okay, so means 4 pairs around the central atom. Lewis has many other, by the way, contributions to chemistry. He gave us the acid-base theory, the Lewis acid-base theory, where acid can be defined as the proton acceptor, electron acceptor or donor. And then it talks about, he has some contributions in dot diagram, Lewis dot diagram, if you remember. Okay, and some contribution in thermochemistry as well. So he has many contributions to the chemistry. But anyway, going back to the ionic compounds. So we talked about why there is a need that they are all trying to get the noble gas configuration. That is called the octet rule. And we all have these ions, you know, positive ions, negative ions. Where did it go? We have a positive ions, negative ions, but these are all called monoatomic ions, like lithium plus 1, calcium plus 2, oxygen minus 2, fluorine minus 1, nitrogen minus 3. This is only one atom. So ions of one atom are called monoatomic ions. But the next thing we talk about are the polyatomic ions. So many ions are made up of multiple atoms with an overall negative charge. There is one polyatomic ion, that is ammonium, NH4 positive ions. Most of them are negative ions. The negative ones are mostly acids, and they have lost their hydrogen atoms. What is talking about is that, like for example, it is a nitric acid. So when nitric acid loses the hydrogen atom, what is left here is negative NO3 minus. Or if you have a nitrous acid, so when hydrogen atom is gone, what is left is nitrite ion. Okay, so if you have a sulfuric acid, okay, if two hydrogens are gone, what is left is sulfate ion. So what it is saying is that they are usually acids who have lost their hydrogen atoms. Um, now let's talk about how do we write formulas of ionic compounds, whether we're dealing with monatomic compounds or polyatomic ions. So I'm sure you all remember this: calcium plus 2, fluorine minus 1. So opposite charges, we do the crisscross method. So 1 goes to calcium, 2 goes to fluorine. We write it as a subscript. Okay, for transition metals with multiple oxidation numbers, we use Roman numerals. So if I have iron 2 phosphate, so let's talk about iron 2 phosphate. So iron 2, this Roman numeral is telling you that the oxidation number of iron is plus 2. And then phosphate, we got to memorize, is minus 3. So 3 goes to iron, 2 goes to phosphate. So it is Fe3 PO4 parenthesis 2. So this is how we write the ionic compounds. So the formula Fe3PO4, the 6 plus charge is from the iron. Iron is plus 2. That's what the 6 plus charge means, that iron is plus 2. If you have iron 3, that means it is positive 6 charge right here. Okay. And then phosphate is minus 3. So when you have 2 phosphates, okay, so that charge is like minus 6. So the overall charge for the formula is 0. So for all ionic compounds, their overall charge has to be 0. Okay. For example, you have K plus and Cl minus. So the formula is going to be KCl. You know, it's one atom of potassium plus 1 charge, one atom of chlorine minus 1 charge. So plus 1 minus 1, they cancel each other, is 0. If it is K2O, so I know that the potassium has the oxidation number of plus 1, oxygen has the oxidation number of minus 2. So what is the charge here? 2 times 2 multiplied by plus 1 will be plus 2, and this is 2 multiplied by 1, you know, they multiply each other, will be minus 2. So that means it is still 0. So all the net charge has to be equal to 0. And I just gave you an example of a polyatomic ion, Fe3PO4 parenthesis 2. I repeat it. Iron, here oxidation number for iron is plus 2. You know, this 2 is going from iron. And I know the oxidation number for phosphate is minus 3. So this, multiply them together, you know, multiply them together. This is plus 6, and multiply them together, this is minus 6. So this is how we do it. You can even figure out, let's say, AlPO4. So let's calculate the oxidation number for each one of them. So aluminum, I know oxygen is negative 2. I know aluminum is plus 3. So this, multiply them together, it's negative 8. This, multiply them together, it's plus 3. So I need to make sure that they are all equal. That means the phosphorus is plus 5. Because plus 5 will make it plus 8. That's what I need to get it neutral. So that means the oxidation state for phosphorus here is plus 5. So this is, you need to know how to calculate the oxidation states. But you also, as I said, you need to know that we do use Roman numerals for transition metals. The next topic is why do we make um, ionic compounds? I'm sure you all know how to name ionic compounds. You know, all monatomic ions end with "ide," and oxy ions. Okay, let me explain this also. Monoatomic anions, and you're naming them. They end with "ide." So oxygen -2 is oxide, fluoride, nitride. They all end with "ide." But the oxy ions, you know, the oxy anions means the anions. Okay, these are monatomic ions, but these are the anions who have an oxygen atom attached to them and they have a charge. They end with 8 or "ite." If they have a higher number of oxygen, it is 8, and if they have a less number of oxygen, it is "ite." For example, PO4 will be phosphate and PO3 will be phosphite. Okay, SO4 will be sulfate and SO3 will be sulfite. So NO3 will be nitrate and NO2 will be nitrite. Again, there are some exceptions. I have a polyatomic ion, not the oxy ion, but the polyatomic ion that ends with cyanide. I have a polyatomic ion that also ends with "ide." So that is the exception to the monatomic ions here. Then, carbonate, there is 8 bicarbonates or hydrogen carbonates. So there are a lot of some, exceptions to these structures. But you basically need to know is that the cations gives the first part of the name. So first of all, you have to write the positive ion and then you write the negative ion. Okay, so the anions give the second part of the name. So it ends with "ide," chloride, fluoride, bromide, nitride. Or complex ions, your polyatomic ions. Okay, so this is calcium fluoride, this is iron 2 because iron is a transition metal. This 2 is coming from iron, so iron 2 phosphate. So you need to do some practice, so you need to deduce the formulas and names of ionic compounds. So at this time you could pause the video and write the formulas. Okay, there is also a worksheet in your packet that has a list of compounds that you need to write the formulas of, and I will be grading it. So what did we learn so far? We learned that ionic bonds are formed by the attraction of oppositely charged ions. They are formed between a metal and a non-metals. Metals make cations, non-metals make anions. So metals lose their valence electrons, non-metals complete their outer shell or octet by gaining the electrons. The number of each ion in the formula is determined by the lowest common multiple of their charge. They're always the lowest ratios. All ionic compounds have empirical formulas. So Fe3PO4 parenthesis 2. This is the empirical formula of this. KCl, K2O, Na2S, whatever the ionic compounds are. All ionic compounds formulas are empirical. Means they are already present in their simplest ratio. You cannot simplify it any further. You remember empirical and molecular formula. Empirical formula is the simplest ratio. Okay, simplest ratio. And molecular formula like I have C6H12O6. I'm just trying to revive your memory. 1 to 2 to 1 ratio. So the empirical formula will be CH2O. So this is for covalent compounds or molecular compounds. But what I'm saying here is that all ionic compounds, their formulas are already in the simplest ratio. Okay, you don't simplify them anymore. Some other things you need to learn about ionic compounds are that what is the physical state of ionic compounds? Physical state of ionic compounds. All ionic compounds are solid. Usually they are solid at room temperature. They are solid at room temperature. They form crystals and melt at relatively high temperature. They have very high melting point and boiling point. And why, I will explain that in a second. They are soluble in water because water is polar. Okay, and I will explain the chemistry of solubility in few minutes. So they are soluble in water. They are, since they have very strong you know in ion interactive forces. So or you call it interionic forces. They're very strong interionic forces, means ions are holding each other very tightly. So because of that, they are very less volatile. As a matter of fact, in industry, the latest research is happening is that they could use ionic compounds as solvents instead of organic compounds because they're not flammable. Okay, they're not flammable. They're very soluble. They welcome everybody, and they have very less volatility. They're pretty stable when you heat them because they're very high melting and boiling points. So because of these properties, they are chosen, or they are being researched to be chosen as a common solvent. Okay, they have a lot of those properties. Now let's talk about why they have high melting and boiling point. So for ionic compounds have a very strong crystal lattice structure. Crystal lattice structure means ions are arranged with other ions. Each ion is holding some other ion, so they are held together by a proper arrangement, a regular arrangement. That regular arrangement is called lattice. Okay, that means every sodium ion has is surrounded by a chloride ion. Okay, so it's like chloride ion here, chloride ion here, then you have a chloride ion here, and a chloride ion here. So and then each chloride ion is going to be surrounded by sodium ion. You see, this is also surrounded by sodium ion. So my point here is that this arrangement is multipolarized. This is a unit cell. This is one unit cell, and then it multiplies. It goes like this. So you can say that each one here is surrounded by this, and then there are some perpendiculars, on this. So each of them is surrounded by 6 chloride ions. Every for different compounds, it's a different number. But for particular, this is the simplest unit of ionic compounds. So for sodium chloride, each sodium atom is surrounded by 6 chlorine atoms. I'm sorry, I shouldn't use the word atom. It's each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. Okay, so this unit structure is called lattice. So overall, this each sodium ion is attracted by the negative ions, and to break this, you need a certain amount of energy. So that energy that we are using to break this one is called lattice enthalpy. The lattice enthalpy is the energy required to decompose 1 mole of ionic lattice into gaseous ions. So that is called lattice enthalpy. Lattice enthalpy is the energy required to break 1 mole of this lattice structure into its gaseous ions, individual ions. And since they are holding opposite ions together, it is very strong crystal lattice structure. That is why ionic compounds do not conduct electricity in solid state, because every it's very hard to do 2 things at a time, spelling and talking. So each ion is kind of bound at their place. They're held at a place. They cannot move around. So since they cannot move around, they don't conduct electricity. They do not conduct electricity in solid state. in solid state. But as soon as we start melting them, first of all, they will melt at a very high melting point because they're holding each other very tightly. That electrostatic attraction is very, very strong. So they're holding each other very tightly. So I have to heat it to a high temperature to separate them. But yes, once it starts melting, okay, molten sodium chloride will conduct electricity. Either I melt it or I dissolve it. Okay, dissolve in water. So when they're dissolved in water, so I take sodium chloride and I put it in water. That water, that H2O, will split this ionic letters into individual ions. It will break it. That, if you remember, this is called dissociation. So each sodium ion will be surrounded by water molecules, okay, and each chloride ions will be surrounded by water molecules. All right, so this dissociation where they are separated by each other, this they become they ionize. Okay, we call them hydrated. No, it is a hydrated salt. So now it will conduct electricity because those ions can travel. They can take the current. They can electricity is basically flow of electrons. So to flow those electrons, you need these ions to go from point A to point B. When they were sitting together as a solid state, they could not go anywhere. But either you melted them, then they are a little bit free to move, and they kind of start ionizing, or you literally dissolve them in water where they do ionize or dissociate. Now they're free to move, so they become good conductors. Okay, they become good conductors once you dissolve them in water. But you need to explain this chemistry of what makes them good conductors here. So you also need to understand that I don't want you to confuse taking sodium atom. We talked about periodicity last unit. We drop sodium into a water, okay, and it will react. So you had to write an equation that metal plus water will make metal hydroxide. Remember that? Okay, so there was a chemical reaction. But when you drop sodium chloride in water, the water basically dissociates it into sodium ion and a chloride ion. You know, it is an aqueous solution. So I want you to understand that this is not a chemical reaction. This is a physical. Okay, this is a chemical reaction. So sodium atom works different with water than sodium ion. There is a difference between the two. They have very different properties. The sodium ions dissolve in water without a chemical reaction, whereas sodium atom produce, this hydrogen gas also. These differences occur because the sodium ion is charged and has a stable electronic arrangement, whereas sodium atom does not have a stable electronic arrangement. Okay, so you must understand that why it is doing what it is doing. So it is because of the stable electronic arrangement we are saying that sodium atom reacts with water, whereas sodium ion dissociates with water, because sodium ion doesn't need to gain or lose anything. It is already pretty stable. So that kind of talks about it. Now we can also talk about how to predict ionic compounds. How do you know that which elements will make ionic compounds and which elements will make covalent compounds? So we know that prediction of ionic or covalent compound is based on electronegativity. Okay, electronegativity is a force of holding a pair, of pulling the pair of electrons towards itself. So electronegativity increases and it decreases down. So greater the electronegativity difference is, like if you have somebody from here and somebody from here, they have very less electronegativity, they have high electronegativity. Fluorine is the most electronegative element. So greater the difference is, more the chances are that it will be a ionic bond. So if the electronegativity difference is from 0 to 0.4, okay, it is non-polar covalent bond, means electrons are being shared. 0.5 to to 1.8 is a polar covalent bond, and greater than 1.8 is ionic bond. So if the electronegativity difference is greater than 1.8, then it is going to be the ionic bond. So this is how you can predict uh, the, the nature of the ions. I think I did not mention here that there is another term that we use here, that when how many ions are surrounded by the other ion, like how many anions are surrounded by a cation, or how many cations are surrounded by the anion. The term that we use for this is called coordination number. So in this case, when I'm telling you that sodium is surrounded by 6 chloride ions and chlorine ion is surrounded by 6 sodium ions, that means for sodium chloride the coordination number is 6. You can only figure this out from the crystal letter structure, okay? Otherwise you would not know it. The other thing we need to know is that the ionic compounds have a very giant structure. This unit multiplies itself and gets bigger and bigger. So they have a very giant structure. This is how this is the terminology you need to know. That a single ionic crystal contains a huge number of ions in the regular operating unit, and this is called known as unit cell. And then there are multiples of those unit cells, so we call it a giant structure. That's pretty much all. Let's see what else is in there for ionic compounds. So this is your homework for ionic compounds. You need to do some research here. This is homework for today. Okay, it is due next class. And then we will go from there. So thanks a lot, everybody. This is all about ionic compounds you need to know. And going forward, we will talk about some covalent compounds. Thank you.